right, all right. Let's get those videos on. Let's get those videos on. I want to see you guys. I want to see you guys. Hopefully some people are going to start showing up here even as we speak. I guess stand up. You're going to need this. Today your brain is going to be unwired. Today I fear I'm going to unwire your brain. So stand up, stretch, because you're going to need it. You're going to need it. Oh. I'm hoping everybody did their job and got outside. I'm hoping everybody did their job, their duty to go outside in this beautiful, beautiful, stunning weather. Okay, let's sit back down. Let's sit back down. I don't know when our next quest will be. It'll probably be next week. It'll probably be next week, quest number 2. It will have a lot to do with the cross product. It's going to have a lot to do with the cross product and probably a little bit with lines and if we're lucky, planes, which would be sections 12.5 and 12.6. For tonight, I want you working on the homework, exclusively on the homework in 12.4. You should almost be finishing up the homework in 12.4, which is about our vector cross product. Okay, where did we leave off last time? Well, fortunately, kind of like a Food Network show. Okay, I've rebaked the cake. Okay, what we were ending with was the norm of A cross B. What we've shown so far is that if I've got a green vector and I've got a blue vector, if I've got a green vector sitting in any orientation in 3-dimensional space, and I've got some other blue vectors sitting in orientation in 3-dimensional space, blue cross green would be where in this room? The vector blue cross green would be where in this room? Would it point up or point down? Would it basically point up or point down? Blue cross green would point down. It would be in this orientation right here, because you would put your right hand on the blue and swing that way, and my thumb would point down. Now, if I did green cross blue, you'd put your right hand on the green vector, swing it towards the blue, and we're at that orientation right there. The red vector is perpendicular to the plane that has the blue vector and the green vector. Any two vectors that aren't parallel are going to define a plane. The red vector points perpendicular to this plane. So red dot green would be what number? Red dot green would be what number? 0. Red dot blue would be what number? 0. Okay? And that's some of the things that we've shown about the vector cross product. That's one of the things that we've shown about the vector dot cross product is that, and I've got it on the board over here as a property. Can you read this to me? Can you read that? I want to make sure you guys can read it. What does that say? Can you read that? Or not? A dot A cross B, the scalar A dot A cross B equals the scalar B dot A cross B, which is equal to the number 0. You guys can prove that. I can ask you to prove that on the second quest. I did ask you to prove for homework, which I could ask on the second quest, that the vector B cross A is equal to what other vector? The vector B cross A is equal to negative A cross B. So it's our first product that's not commutative. That's not commutative. If you take the cross product of two vectors and you get 0, you get the 0 vector, 0, 0, 0 coming back out, what does that tell you about your two vectors? They're not perpendicular. If they're dot product, if A dot B was 0, they would be perpendicular. If A dot B would be 0, they'd be perpendicular. But if their cross product is the 0 vector, what does that imply about the two vectors?
The determinant is 0.
The determinant would be 0. I like that. I like that if we were looking at that I, J, K, A1, A2, A3, B1, B2, B3. This implies that A is parallel to B. That implies that A is parallel to B. You're not getting a cross product out of it. You're not getting a cross product of any height out of it. These two vectors have to be in the same, have to be scalar multiples of each other. Which implies, now here we get ready for what's the definition of two vectors being parallel? Ooh, Dr. One, I hate this already. What's the definition? What's our definition that the vector A is parallel to B or B is parallel to A?
You can multiply a scalar times one of them to get the other one.
Very good. That B is equal to alpha A or A is equal to alpha B. I proved, and it took probably 20 minutes. I invested probably 20 minutes of the last class proving that the cross product is distributed. We've got a vector addition, and if I look at this, that A cross B plus C is equal to the vector A cross B plus the vector A cross C. I asked you guys to prove that if you have a scalar alpha times A cross B, that is equal to A cross the scalar alpha times B, and it's also equal to, I didn't ask you to prove this, the scalar times A cross B. So if you have like 5 times A cross B, if you have 5 times A cross B, it's the same thing as 5 times A cross B, or it's also equal to A cross 5 times B. The scalars commute with everywhere across that cross product. Okay, now Lagrange's identity. Do not look at the board. Do not look at the board. Do not look at your notes. If I ask you something on Quest 2 about Lagrange's identity, it tells me that the norm of A cross B squared is equal to, the norm of A cross B squared is equal to the what? What's in your gray matter? What's in your gray matter? The norm of A cross B squared. Be a great true-false question. All I got to do is change
the norm of A squared times norm of B squared?
Perfect, perfect. That's the first term. Now, is it a plus or minus? Is it a plus or minus?
Minus.
Minus. And what's the last term? What's the last term? Do you have anyone?
Is it sine squared?
That's where we end up, Josh. That's where we end up. But if I ask you guys to derive it, you're going to want to remember Lagrange's identity. And I have it written on the board here, cleverly called Lagrange's identity. The norm of A cross B squared is equal to the norm of A squared times the norm of B squared minus A dot B squared. Minus A dot B squared. So if I ask you to prove that the norm of A cross B is equal to the norm of A times the norm of B times the absolute value of the sine of theta. Dr. Woods, you're saying too many words. If I ask you to prove number 1, read number 1 to me. Read number 1.
The norm of A cross B is equal to the norm of A times the norm of B times the value of sine theta.
That's very, very good, Stuart. That's what we're trying to show. That's what we're trying to show. We start with you start with, and I'm just helping you out in case we put this on the test, you start with whose identity? You start with whose identity? You start with whose identity? Lagrange. How screwed are you if you don't know Lagrange's identity? How screwed are you at that point in time? Very screwed. If it's a 10-point problem, you might as well just say, I'm screwed. I just got screwed out of 10 points, okay, if you don't remember Lagrange's identity. Because there's no way you're going to pull out the rest of it if you don't have this. The next thing that you do is we proved in this class that A dot B was equal to what? We proved that A dot B was equivalent to what? First quest. We proved that A dot B was equal to what? Definition is A1, B1 plus A2, B3 plus A3, B3. But we proved using geometry that it's equal to the
norm of A times.
norm of A times the norm of, I'll keep going, B times the cosine of theta. And that's what we're using here. Again, it should be in your notes. We're replacing A dot B from Lagrange's identity with the norm of A times the norm of B times the cosine of theta, and we just squared everything. That's the next step in the argument. And again, this should be in your notes. And again, you should have gotten this last time. Then what have I done to go from this step to this step in the argument? What have I done to go from this step to this step in the argument? What have I done to go from this step, this line of logic, to this line of logic in my argument? Factored. All I did was say, hey, you're alike in both of these. Let's pull this out. And then you're left with 1 minus cosine squared. But 1 minus cosine squared is sine squared. And so now I'm here. And then essentially what I'm doing is taking the square root of both sides. It's not that hard of an argument. Now, just making sure. The square root of 5 squared. Well, 5 squared is what? Dr. Warren, quit yelling. 5 squared is what?
25.
Square root of 25 is 5. The square root of negative 5 squared. Well, negative 5 parentheses squared is 25. The square root of negative 5 squared is 5 also. So the square root of ice cream cone squared gives you the same result as the absolute value. Whether it's positive or negative, whether it's 0. The square root of something squared is the same thing as the absolute value. And so that's why we're getting the absolute value of the sine of theta. Okay. Stand up again. I can already tell you need it. Stand up. Stretch. It's going to be a long day of art. It's going to be a long day in art class. Oh. Okay, slap your face. Say, wake up. Say, wake up. Okay, sit back down. Okay, A dot B is equal to the norm of A times the norm of B times the cosine of theta. I've drawn 2 vectors, you draw these vectors. I've drawn 2 vectors, you draw these vectors. A dot B is equal to the norm of A times the norm of B times A dot B is equal to the norm of A times the norm of B times the cosine theta. Where's the angle theta? Mark the angle theta in the geometry. And hopefully you put it as the angle between the 2 vectors. Now I've got to ask, if the dot product is 0, and the dot product is equal to the norm of A times the norm of B times the cosine of theta, these guys are positive. Those guys are positive. The 0 is coming from this guy. What angle makes cosine 0? What angle makes cosine 0 for the third time in this class? What angle makes cosine 0? Pi over 2. Does it make sense if the dot product is 0, the vectors are perpendicular? Does it make sense if the dot product is 0, that the vectors are perpendicular? Yeah, so it makes sense. Now what I want you to do is drop a perpendicular, kind of like you were going to lay in a parallel and a perpendicular, but you're not. Drop a perpendicular from A down onto B. Drop a perpendicular in your drawing from A down onto B. Mark the right angle. Mark the right angle. Okay, now this is again active learning. Give me an expression that represents the hypotenuse in that right triangle you just created. Write down an expression that represents the length of the hypotenuse in that right triangle you just created. Okay, this is what I'm hoping. This is what I'm hoping you guys have. This is what I'm hoping you guys have. I hope you did this. You've got that. I'm hoping you've got that. And then I'm hoping you wrote this here. Did anybody do that? Did anybody do that? Did anybody do that? Okay, now, write down an expression that represents the length of that altitude, that leg, this altitude, this leg of the right triangle. Write down an expression that represents the length of that altitude using trigonometry. Okay, I'm not going to answer that question right now. Okay, look up at the board. Look up at the board. Okay, I've got this. This green vector is my b vector. This green vector is my b vector. If I moved it out here, would it still be the b vector? Would it still be the b vector? Okay, right here is the b vector. If I move it here, would it still be the b vector?
Yeah.
Okay, it's still oriented the exact same way in three-dimensional space. If I slide it up to there, would it still be the b vector? If I slid it up to there, would it still be the b vector?
Yes.
Draw that b vector. Draw that b vector in your diagram. Draw that b vector in your diagram. Okay, now I've got my a vector. I've got my a vector. I got my a vector. If I would slide the a vector over to here, would it still be the same a vector? Would it still be the same a? If I've got my a vector here and I slide it over to there, would it still be the same a vector? Would it still be? So draw that a vector. Draw that a vector again. Okay, now what I want you to do is go to grid view. What I want you to do is go to grid view, change yourself to grid view, and then I want you to hold up your diagram that you've been drawing. I want you to hold up your diagram nice and still so that Dr. Warren can see what you guys have. Ooh, Rhett, I like your drawing. Stuart, nice drawing. Cosmo, great drawing. Yeah, you guys are drawing good pictures there. Awesome, awesome. You guys own this. Okay, good. I'm seeing lots of good things. Is this vector parallel to this vector? Is this vector parallel to that vector? Is that vector parallel to that vector?
Yes.
You're like, Dr. Warren, I don't know if two vectors are parallel. Oh, one's a scalar multiple of the other. Is B a scalar multiple of B? Is B a scalar multiple of B? And you're like, yes, one. One is the scalar. One is the scalar. This is the vector A, and so this vector is parallel to that vector. Back in geometry, make your geometry teacher so proud of you. What shape is that? What shape is this? What shape? It's all in the word parallel. Parallelogram. Say that. Parallelogram. Okay. How do you find the area of a parallelogram? How do you find the area of a parallelogram? You make your geometry teachers proud. If you have a parallelogram, how do you find the area of it?
Find the area of two triangles and then the rectangle in the middle.
Yeah, you could find the area of the two triangles or the rectangle in the middle. And write this down. Base times height. Write this down. Base times height. But I like the way Nick is. Nick's given us the geometry that goes with it. I mean, imagine this. Imagine this. Imagine that I've got this right triangle here, where I've just dropped that altitude. I've got this right triangle. Take out your jigsaw. Take out your jigsaw. Take out your jigsaw. Hold up your jigsaw. Okay, we're gonna cut this wooden parallelogram and cut this side off. So we're gonna do that. So let's go. Come on, let's go. Now I'm gonna take this wooden triangle and I'm gonna move it over to there. I'm gonna take this wooden right triangle and I'm gonna replace it over there. Draw that, draw that, draw what I just said. You've got this wooden right triangle and you're gonna replace it over there. Okay, so this is basically what we have. You can kind of see my dotted line. You probably can't see it. It probably doesn't look like anything. I got my dotted line here, which kind of represents this triangle. I moved it over to here. I moved it over to here. I moved it over to there. Now, what shape is that? What shape is that? What shape is that shape that's left over? What's that shape the moment we move this right triangle over? What shape is that?
Rectangle.
A rectangle. Now, how do you find the area of a rectangle?
Base times height.
Base times height, length times width. What did you guys have? What did you guys have for this width? What did you guys have for that width? What value did you have? Some of you guys, I looked, some of you had it. It was look at the right triangle, the hypotenuse is norm of A. The angle is theta. Is this side the opposite side or the adjacent side to the angle? Is this side the opposite side or the adjacent side? Opposite. So you should have had the norm of A times the sine of theta. And we're assuming theta is positive. We're assuming sine's positive here. We're in the first quadrant. Okay, what expression represents the length? What expression represents the length of that rectangle? What expression represents the length of that rectangle? And again, what I've done is cut off this and moved it over. What expression represents the length of the rectangle that we created? Norm of B. This is still the vector B. So this would be the norm of B. This would be the norm of A times the sine of theta. So what would be the area of that parallelogram? What would be the area of that the area of this rectangle, which is equal to the area of this parallelogram? How do you get the area of a rectangle again?
Base times height.
Base times height. So my base is the norm of B. My height is the norm of A times the sine of theta. So my area would be base times height, the norm of B times the norm of A times the sine of theta. We haven't lost any area with the jigsaw. We haven't lost any area of the jigsaw. So the area of this parallelogram, so shade your parallelogram. Shade your parallelogram. Shade your parallelogram. Draw an arrow pointing to your area, and then write down the norm of A times the norm of B times the sine of theta. And we're again assuming this is positive. Theta, sine of theta is positive. Now, do you see this expression anywhere else in the room? Do you see this expression anywhere else in the room? Do you see this expression anywhere else in the room? And you're like, oh, damn it, Dr. Warren, it's the same thing as the norm of A cross B. The norm of A cross B. So write this down. The norm of A cross B, you don't need to write this next word. Geometrically, don't write that down. The norm of A cross B geometrically is equal to the area of the parallelogram that naturally follows from A and B. So the norm of A cross B is equal to the area of the parallelogram described by A and B. All right.
So how is that related to the dot product? So the A dot B cosine theta stuff. Cosine sine, so how is that?
Who's asking that? Michael, is that you?
Yeah.
Yeah, Michael, great question. I can't wait to answer that question. Okay, I can't wait to answer that question. But we're not quite ready. Draw two vectors, arbitrary vectors, and mark with their butts together, We'll orient them that way. We'll make them direction vectors. We'll pretend they're at 0, 0. Okay, draw two vectors, two arbitrary vectors. Mark one as an ice cream cone vector and the other as a smiley face vector. Mark one as an ice cream cone vector and the other as a smiley face vector. Now, draw the natural parallelogram that follows from those two vectors, your ice cream cone vector and your smiley face vector. Draw Okay, now shade lightly the area of the parallelogram you just created. Draw an arrow to that area. Now give me an expression that represents that area. Give me an expression that represents that area. A simple expression that represents that area in terms of the vector products that we've been dealing with. And what do you guys have? What do you have as the area of that parallelogram? What expression represents the area of that parallelogram?
Norm of ice cream cone cross smiley face.
The norm of ice cream cone cross smiley face. The norm of ice cream cone cross smiley face. Okay, you're like, well, Dr. Warren, like, could you give me some kind of physical thing that I can hold on to other than geometry? What's the point of something like this? Well, imagine that I've got two vectors. Imagine that I've got two vectors, okay? And I've got them oriented like this. And I could talk about the parallelogram that I'm dealing with. Now imagine that this is the motion of something. This is the motion of something. And the blue vector represents a force that I'm going to apply to an object moving in that motion. Okay, so what's going to happen is I've got something moving along the green vector, and I'm going to apply a force. Now again, where I move the vector, the blue vector doesn't, let me see if I can get this. Right, where I move it doesn't matter. If I move it up here, like this, and I'm applying a force, part of this force is going to cause this object to rotate. Does that make sense? If something's moving this way and you apply a force to it that way, as it moves, part of what's going to want to happen is it's going to want to torque or move in a direction this way. Well, Dr. Warren, what plane does that lie in? Well, it lies in the plane of my two vectors. The rotation goes around the cross product vector. If I do blue cross green, it's going to go that way. Now, if I did green cross blue, it's a little bit hard for me. I can't wait till October 5th. Okay, come with good masks, because some of you guys are going to be at the front of the room holding vectors, holding rope. You're going to be holding sheets in the air. You're going to be doing all kinds of stuff, because I only have two hands. I have my two vectors. Okay, but if I said green cross blue, would the vector point up or down? If I said green cross blue, would the vector point up or down? You got to know this. Green cross blue, up or down?
Up.
Up. Blue cross green. Well, that's easy. Down. Okay, so if I'm thinking about my force, if I applied a green force or a blue force moving in a certain direction, the sign of my cross product tells me which torque I'm going to be applying, whether I'm going this way or that way. Does that make a difference in electricity with electric motors? If you wrap the wire this way or you wrap the wire that way, do you get a different action taking place when you apply electricity to that wire? Okay, and this is what the cross product's actually able to give us. The motion is in the plane. The orientation is around an axis that lies perpendicular to that plane. And it's the direction of the torque. Write that down. It's the direction of the torque. The magnitude of the torque, the amount that you're applying, is the magnitude of that cross product vector. So when you see the cross product in engineering, when you see the cross product in physics, when you see the cross product in chemistry, almost all the time it's talking about an angular quantity. It's talking about an angular momentum or something moving. You've got your angular momentum and your linear momentum. The cross product describes I'm helping you out. The cross product describes the angular. The dot product describes the linear. Now, as a mathematician, geometrically, the norm of the cross product represents the area of the parallelogram that naturally arises from the two vectors. Whew. Stand up again, stand up again, stand up again. Stretch. Okay, sit back down, sit back down. Look at your watch, look at your watch. What time does class end? What time does class end? What time does class end? Look at your watch. 11. What time is it now? What time is it now?
10:20.
10:20. Okay. Woo! Okay, now I've got a shape for you. Look at this shape. The base is the same as the height. I mean, the base is the same, the bottom's the same as the top. This side here is the same as this side back here, and this side is the same as this side. Okay, what is this shape called? Does anybody remember what this shape is called? It's not a box, okay? What is this shape called? Does anybody remember what this shape is called from geometry? That's what I thought. Okay, so here's a new word.
Parallelepiped.
There we go. Awesome. I don't know who said that, but very good. Parallelepiped. Say it. Not profanity. Okay. Say parallelepiped. Hands on the space bar. Hands on the space bar. Say parallelepiped. Okay, let's try that again. Hands on the space bar. Hands on the space bar. Say parallelepiped. You're gonna hate me. Dr. One, we already do. Right. Look, if two vectors naturally describe a parallelogram, then three vectors in three-dimensional space naturally describe a parallelepiped. Okay? And so we can imagine, now just imagine, I've got my vector A maybe going like this. I've got my vector B. Now guys, this is kind of being drawn into the plane. This is kind of being drawn in. This has got some perspective to it. Then I've got the natural parallelogram that comes from A and B. Then I've got some other vector, I'll put my B down here. I've got some other vector C, like this, and imagine sliding this parallelogram along C. Imagine sliding this parallelogram along C. This is the same thing as taking like a square and sliding it straight up. And when you do that, you're going to create a box. You're going to create a box. How do you find the volume of a box? How do you find the volume of a box? These are simple things from elementary school. How do you find the volume of a box? Length times width times height. It's also, you can also find the volume of a parallelepiped. You can also find the volume of a parallelepiped by talking about the area of its base times its height, which would be the distance between the top of the parallelepiped and the bottom of the parallelepiped. If you went straight down, what's the distance between these two parallelograms? That's the way you find the volume of a parallelepiped. Now, I am not going to make you draw this, but essentially what you would do is you would redraw the vector C at all the corners here. And then you would redraw the parallelogram up here, which then would give you some visual representation of that parallelepiped. Dr. Warren, what the hell are we doing? What does this have to do? Well, get ready to write something down. Get ready to write something down. What if you've got What if you have that? So can you read that? Can you read that? Can you see that? What does that say? I just drew it on the board. What does that say? What does this say?
E dot A cross.
C dot A cross B. Okay, you got to write down one word. scalar or vector? Write down the word. Is the result a scalar or a vector? Write down the word. And I'm hoping everybody wrote down the word scalar. It's a scalar. Now this is kind of beautiful because it's bringing our two products together. This is my,
Dot product.
and this is my
Cross product.
cross product. We know there has to be some wonderful geometry here. We know there has to be wonderful geometry. Okay, now, put your hands together like this. Put your hands together like this. Then bring your knee up to meet your hands. Then bring your knee up to meet your hands. Okay. Now, stick your leg out. And there's your three vectors. You're like, what the hell, Dr. Warren? No, this is Karate Kid. This is Karate Kid. Okay, so now, that was horrible. Let's do it this way. I've got my three vectors. I've got my three. I can't wait for you guys to get back in the classroom because these look so, the fish eye in this thing makes it. But I've got my three vectors. I've got my three vectors sitting here in three-dimensional space. I've got my three vectors sitting here in three-dimensional space. Can you kind of visualize a little bit the parallelepiped? Can you kind of visualize if I created my parallelogram and then slid this to all of my corners, the parallelepiped that I would create, Good, I can tell you can. So let's do it here, Let's imagine that this vector right here is my vector A. This vector right here is my vector A. So I've got a vector here. The red vector is my vector, the red vector is my vector, the red vector is my vector A. I've got another vector back here. I've got another vector back here that's my vector B. And then I've got my vector here, that's my vector. I've got my vector here, that's my vector C. Okay, so this is my drawing I have. Have you guys drawn this? How many people have drawn that? How many people have already drawn what Dr. Warren drew? Okay, to the best of your ability, to the very best of your ability as artists, try to mark the vector A cross B in that drawing. Try to mark where the vector A cross B would be in that drawing. If I'm looking at this as being my drawing, where's the vector? Draw the vector A cross B. Okay, go to grid view, show me your art. Go to grid view, show me your art. I want to see your art. What do you got for art for me? What do you got for art? Let me see your art, guys. Yeah, baby, you guys are good. Okay, so I want everybody over here to look at Rets. Look at what Red has there. Stuart, hold yours up too. If you look at Rets, he's got the vector A, he's got his vector B, then he's got A cross B. So put your right hand on Rets A vector, Rets A vector and swing it towards B. Do you see why it points up? It's perpendicular to the plane. Okay, make me number one. Thanks, guys. So if I'm thinking, I know that from this, it doesn't matter what I say now. I can say whatever and you guys won't. Oh. now you'll focus. Okay, so now, okay, if I come back over here, A dot A cross B is equal to B dot A cross B, which is equal to, don't break the camera, which is equal to 0, which means the cross product vector is perpendicular to,
A and B.
very good, Gordon, A and B. Now I'm gonna take off my dress. Oh. Oh. And so that's why Rhett drew it pointing up. Now it's A cross B versus B cross A, which would go straight down. So draw a little right angle in there. Draw a little right angle from your cross product to your A, and then try to draw it in perspective, a right angle going back into space between B and A cross B. Okay, now get ready to weep. Because I'm going to ask you to do something. Using the law of cosines, the result we had from the law of cosines, give me another expression that would be equivalent to C dot A cross B. Give me another expression that would be equivalent to C dot A cross B. Okay, now I'm going to play singles. Okay, Caitlin, what do you have for me? Caitlin?
So I think it would be C dot, the norm of A times the norm of B cosine theta.
I like that, but I instead of C dot, let's just go with the norm of C. And then we have the norm of A cross B, which is perfect, and then the cosine of theta, which is perfect also. So let's give it up for Caitlin. Come on, I want to see those hands clapping. You're glad I wasn't calling on you. I'm glad I wasn't calling. Okay, now, it's going to hurt. Theta would be the angle between, in this case, theta would be the angle between what? Mason, you got anything for me, Mason? If you're looking here, C dot A cross B is equal to this, but geometrically, I need to know where that angle theta is. Where's that angle theta, guys?
Is it the angle between the vector C and A cross B?
Very good, Gordon. It's the angle between the vector C and the vector A cross B. Mark that in your diagram. Try to mark theta in your diagram. Okay. So again, if I have my parallelepiped here, this is the vector A down here. This is the vector B over here. This is the vector C. A, B, C. This red vector here would be which vector? This red vector would be which vector, guys? This red vector would be A cross B. Okay, so now theta would be the angle between this red vector and this vector here. I know it's hard because of the camera, but I've got this vector sitting perpendicular, and my theta, feel like I'm playing the violin. Okay, Calc 3 violin. My theta is the angle between here and here. My theta is the angle between, if this is my C vector, and this is my cross product vector, my theta is this angle right here between there and there. And I'm hoping in your diagram that you drew that right there. I'm hoping in my diagram you drew that right there. And you're like, well, Dr. Warren, why do I even care? Well, imagine I want to get the height of this parallel pipet. Imagine I want to get the distance. I want to get the distance from this top plane to this bottom plane. I want to get this distance, this perpendicular distance from here, from my finger up to this plane up here. I want to find that distance. But that would be exactly this distance from here to here. This would be the distance from here to here, which is a little hard to see here. But let's go back to my visual. Sorry. Holding a parallel pipet is hard. So I've got my cross product vector. And I'm looking at this right triangle that I just created with this blue thing. I'm looking at this right triangle which I just created with this blue thing, and I want the distance where my hand is from there to there. I want the distance from where my hand is from there to there. The angle between this side. Oh, I so wish you were here. The angle between my vector C and A cross B. We mark that as the angle theta. I've got my right angle here. Here's theta. This is C. C's the what in that right triangle? C's the what in that right triangle? What is C in that right triangle? The hypotenuse. How long is the hypotenuse? How long is that side of the parallel pipet? What expression would represent how long this side is in this right triangle?
The norm of C.
The norm of C. So mark it. Mark it as such in your diagram. Mark it as the norm of C. This is the side I'm interested in. That distance represents the height of my parallel pipet. That distance represents the height, the distance between the top and the bottom of my parallel pipet. In terms of trigonometry, with my right triangle, the hypotenuse is the norm of C. What represents this distance? Write down what you've got. Gotta write something down there. Write something down there. What represents the height of that parallel pipet? Okay, go to grid view, go to grid view, go to grid view, go to grid view. Okay, show me what you got. Show me what you got. Let me see what you guys have. Let me see what you guys have. Let me see what you have. Cosmo, awesome. I can't quite see your Stuart, sorry. Red. I like what we're going there. Okay. Cosmo, hold your up again. Cosmo, hold your up again. Okay, everybody look at Cosmo. What does he have there? What does he have there? Cosmo, where's your height again? What does he have as the height? So you guys see what he has? What does he have? What does he have?
Norm of C times the cosine of theta.
Norm of C times the cosine of theta, and that's exactly right. So if you're looking up here, the height of this parallelogram, the theta, is it the adjacent side or the opposite side of the angle? In the right triangle, is it the adjacent side or the opposite side of the right triangle? The adjacent side, so it's going to be the hypotenuse, the norm of C, times the cosine of theta. Okay. Shade in, and don't swear. Shade in as much as you can the bottom of the parallelepiped. That parallelogram that represents the bottom of the parallelepiped. Shade that in your diagram. Shade in that, and write down an expression that represents the area of that parallelogram. Write down an expression that represents the area of this parallelogram. Write down an expression that represents the area of that parallelogram. And what do you guys have? What represents the area? What represents that area, guys? What represents that area? Anyone? What represents that area?
Norm of A cross B.
The norm of A cross B. So the norm of A cross B is the area of the base. The height of the parallelogram, Cosmos gave us as, Cosmo gave us as
Norm of C times cosine of theta.
norm of C times the cosine of theta. So what's the volume? What expression represents the volume of my parallelepiped? What expression represents the volume of my parallelepiped if it's base times height? What expression represents the volume of my parallelepiped? Anyone? It'd be the
Norm of A cross B.
norm of A cross B times,
The norm of C.
so norm of C times the
Cosine.
cosine of theta. Do you guys see this anywhere else in the room? Do you see this anywhere else in the room? Oh, Dr. Warren, that's what we got from our law of cosines. So what does this scalar relating our dot product and our cross product represent? What is this scalar? This scalar bringing our two products together represent?
The volume of the parallelepiped.
The volume of the parallelepiped that naturally falls from the geometry of having three vectors. Okay, yeah, but guys, it represents so much more. It represents so much cooler stuff. Because, for example, if you have three forces in three-dimensional space, okay, you've got a force going this way, you're going to apply a force going this way, you're going to apply a force going that way, and you're going to apply another force going this way. You're not only just going to get, if you hit it with three different forces, it depends which orientation you hit them with. You're going to get it going, it's going to be moving, you're going to get it spinning, and then you're going to hit it again, and you're going to get it spinning away in three-dimensional space. And this is where we get up with this idea of a right-hand screw and a left-hand screw. That if you hit something with three forces in three-dimensional space, you get it moving, you get it spinning, and then you get it spinning off in a certain direction. We call a right-hand screw kind of based off what we have with our right-hand rule. I drew these like they're perpendicular, but it still works the same way. If I do A cross B and my C vector lies above the plane, that's called a right-handed orientation. You hit it with A, then you hit it with B, you're going to get that spinning this way, and then when you hit it this way, it's going to spin up along like that. If I apply the force like this, then I've got my, if my other force is this direction, I've got my A cross B, which is still like this, but now I'm applying a force this way, so it's going to be spinning this way, but I hit the force this way, and then it's going to be moving through space in that direction. And we call this a left-handed. We call this a left-handed orientation. Okay, because if I think about my A cross B, and I look at this angle, this is theta. It's A cross B, and there's C down there. Is that angle more or less than pi over 2? Is this angle more or less than pi over 2?
More.
More. Cosine in the second quadrant. Cosine in the second quadrant. Positive or negative? Positive or negative? Cosine in the second quadrant. Positive or negative? Negative. Okay, so this is what I want you guys to think about. If C dot A cross B is positive, you have a right-handed screw orientation being applied to the object. So if this ends up being a positive quantity, you end up with a right-handed screw orientation being applied to the object. If it's negative, you're going to end up with a, I mean, it's not hard. Once you know one's right-handed. If it's negative, then you are going to end up with a left-handed. If it's zero, if it's zero, well, if I come back here, if C dot A cross B is 0, what does that tell you about the vector C and the vector A cross B? Focus. If go ahead, Robert. Is that? They're perpendicular. So if I'm thinking about this, here's my A cross B vector, and then if I'm thinking about it being perpendicular to C, I'm thinking about it lying perpendicular to C, then it's got to lie in the plane that do not mess up your drawing. Do not draw on your drawing. If it's perpendicular, all the vectors that are perpendicular lie in this plane. All the vectors that are perpendicular, if I've got my plane, now this is not quite A cross B the way I've drawn it there, but I've got this. If I look at any other vector that's perpendicular to this blue vector, all of them have to lie in this plane. All of them, Nick, are you following, man? Nick, are you asleep? Okay, good. They all have to lie in this plane. So if I'm thinking about if this product is 0, then C lies in the same plane as A cross B. When you do A cross B, you get this thing spinning. If you hit it with another force that's in the same plane, you're not going to cause it to fly off in space one direction or another. You're going to make it move in that plane, but you're not going to break the plane. So you're not going to get a right-handed screw or a left-handed screw in what's going on. So let's think about this. You have 3 forces that you're going to apply to an object. Imagine that they look like this. I'll give you A and B. I'm going to apply a force A. I'm going to apply a force A, and then I'm going to apply a force B. So I'm going to apply a force A, and I'm going to apply a force B. I'm gonna apply a force A, and then I'm gonna apply a force B. Which direction will it spin? You've got this is in some way, I've got an A going this way, and then I'm going to apply a force B going back into the blackboard. I've got a force A, which is kind of coming out of the blackboard a little bit. It's lying in this plane. Unfortunately, I don't have it drawn well here. I've got this as B. Imagine this is A, and this is B. This is kind of the way I've got it. This is A. You're like, why the hell did you mark this B, Dr. Warren? This is not good teaching. Okay, this is A, this is B. You apply a force this way, and then you're going to hit it with a force this way. What kind of spin will you have? Counterclockwise or clockwise in the plane? If you're going to apply a force A, and then you're going to hit it with a force B, are you going to are you going to go this direction counterclockwise, or are you going to go that direction clockwise? You're going to go counterclockwise. You're going to go counterclockwise. Okay, if I apply a force here, hitting it this direction, and I don't use another force, it's just going to move down in that direction. But then I said, no, you're screwed. I'm going to run a car into you this way. Bam! Okay, then suddenly you're going to start spinning this direction. Now, would it be different if I, first of all, applied a force A, so you're moving that direction, and then I slammed it with a force B? Then you see your orientation is going to go in the other direction. And the cross product grabs that. That sign switch grabs that. Now, imagine that I apply a third force C. So I've got A cross B. So I'm moving this direction, and I don't tell you, I don't draw the third force. But you calculate this, and you get the number 15. You calculate C dot A cross B, and you get the number 15. I've got this thing, now I've hit it. It's now spinning this direction in this plane. This is A, this is B. I'm spinning this direction in this plane. Are you going to be spinning up or down? Are you going to be spinning off in three-dimensional space up or down? Up. If it was negative 15, down, so it'd be going this way, and then this direction, that would be left-handed. If I hit it this way and go this direction, that's right-handed. If it was 0, what does that tell you about that force? What does that tell you about that third force C? If the dot product is 0, what does that tell you about that third force C?
It won't force it up or down.
It won't force it up or down. It's like you're sending a third car in the road. You're sending a third car in the road. Will it cause more damage? Oh yeah, it's gonna be fun, okay? But it's not gonna cause it to go off in three-dimensional space. I mean, guys, do you see how this can be a tool? I mean, this is what I want you to get. When you talk about the geometry, you're like, okay, parallelepiped, worthless, parallelepiped, parallelogram, blah, blah, blah. I don't care, I'm not building parallelepipeds. But when we talk about forces, and like all the crap that's in physics, I mean, in chemistry, quantum mechanics. I mean, okay, well, enough. I gotta stop. Okay, stand up. Stretch. Okay, sit back down. We're going to finish class with this. I've got 5 minutes. What did I just write down? Are you going to take all of my 5 minutes to answer this question? What did I just write down?
A cross B cross C.
Okay, vector or scalar? Is the final result a vector or a scalar?
Vector.
A vector. Okay, now, make that your vector B, make that your vector B. Make that your vector C. And again, we're kind of pretending it's lying in a plane. It's kind of pretending it's lying in the plane. Draw the vector B cross C. Draw the vector B cross C. We're assuming that this lies in a plane. We're assuming that we've got something kind of oriented like this. We've got something kind of oriented like this. It's, you know, we've got our B vector and then our C vector here, our C vector there. Draw B cross C. And what I'm hoping is you guys drew a vector that's coming straight off of that plane that the two vectors are in. I'm hoping that you're drawing a vector going straight up off of that plane. And I guess I'll go right through mine. So it's perpendicular to both of those. This is my B cross C vector. Now what I want you to do is draw a vector A. And let me try to draw it, give you it here in three-dimensional space. That's not perpendicular to my plane. That's not perpendicular to my plane. This one's perpendicular. My red vector is perpendicular, but this blue vector I've just thrown up as A is not. This blue vector I've just thrown up as A is not. It's so hard to see. So I've got a vector that's kind of pointing like this. It's kind of being lost in the camera. Is like this. And now I'm looking at the vector A cross B cross C. And let's just call it D. Well, what do I know about D dot A? If D is equal to A cross this vector B cross C, A cross B cross C, what do you know about D dot A? What do you know about D dot A? So let's go back to this. If you've got B cross C, and you dot it with C, what are you going to get? If you've got B cross C and you dot it with C, what are you going to get? What are you going to get? What's the angle between C and B cross C? What's the angle between C and B cross C? Because you're going to get this. Pi over 2, 90 degrees. What's the cosine of 90 degrees? What's the cosine of 90 degrees? 0. So C dot B cross C has to be 0. Because it's equal to the norm, it's equal to the norm of B cross C times the norm of C times the cosine of theta. But the angle between them is 90 degrees. It's 0. And how about B cross C dot B? How about B cross C dot B? What's that equal to? What's B cross C dot B? What's that equal to?
0.
0. Once again, they're perpendicular. So now I ask this, and I guess we'll just finish. If D is equal to A cross B cross C, if D is equal to A cross B cross C, what is D dot A?
0.
0. Now this is going to be a little bit more miserable. What's D dot B cross C? Okay, you guys look like Ali. You look like Ali at the end of Foreman Ali. Okay, the Thriller in Manila. You look like Ali. You look punch drunk. We will pick up with this on Wednesday. The geometry of A cross B cross C. Okay, you can leave if you can answer this. If you have three vectors, A, B, and C, what does C dot A cross B represent geometrically? Like I said, Ali at the end.
The screw orientation?
Well, it does represent the screw orientation a little bit. Yeah, but geometrically, what does it represent? The volume of the
Hello, pipe.
parallel pipet. The volume of the parallel pipet. Say that.
Volume of the parallel.
You can go. I will see you Wednesday. Come back.
Thank you.
Thanks, guys.
Hey. Hey, Dr. Warren, for my homework, it didn't, it's not there. It says there's like nothing. Or 12-4.
So what I want you doing, is that Michael? Michael,
Yeah.
so what I want you doing is
Oh,
I
there's
want,
the proofs?
no. There's an announcement that has textbook homework for the entire chapter.
Yeah, oh, it's not on WebAssign.
It's not on WebAssign yet. I'm gonna put up a WebAssign later today, but yeah, it's not on WebAssign yet. I want you working on the homework in that handout.
The textbook, okay. All
Yeah,
right.
homework, textbook homework.
All right, yeah, you have a good rest of your day.
Oh, you too, Michael.
Well, that's it.
How are you doing, Mason? I think you're frozen, Mason. There we go. I'm a failure. I just can't believe I get so far behind. Are you wearing a desk? Stop that. I know, I was wearing a desk. That's why I'm behind.